last lesson for this week is simple harmonic motion with dynamics and energy considered. So we've talked about the conservation of energy, the law of conservation of energy last week. And so now we can apply those ideas to pendulums and springs. So simple harmonic motion. So we can understand the motion of a pendulum as an application of dynamics or as an energy system. So consider a pendulum mass, also called a bob, that is initially hanging in the equilibrium position, so not moving. Note that Fg cancels the tension force here. There's no spring force. Remember, this is a pendulum. The net force is 0. Therefore, this is not accelerating. The total mechanical energy for the pendulum is also 0. It does not have any potential energy. It doesn't have a height, nor does it have any kinetic energy. When we move the mass from its equilibrium position to an angle of theta, okay, so that's the pendulum here, and then release it. The force diagram here indicates that force of tension is no longer absolutely in opposition of Fg. So Fg is directly south of our bob. Tension attaches to the point from the bob. Therefore, we need to once again break gravity into its components. The angle that the bob is held at here is the angle at which gravity and its components are in. So if you break up the force of gravity into either F of y, F of x, F parallel, and perpendicular, it doesn't matter what you call them here, we can see that F of y, as labeled here, will be in direct opposition of Ft. So if we added Ft plus Fg, I should say y, that would be 0. Okay, it is not accelerating up or down from here. However, what we do notice is that there is an unopposed force, F of x here. So Fgx is equal to our net force in this case. This is the way that it will accelerate. We know that the bob will accelerate back towards its center position. So this is how we got F of x, which is, again, also equal to F net. So we call this the restoring force that acts towards the equilibrium point. If we'd stretched the bob this way, we would have had a restoring force towards the center again anyways. So the bob accelerates towards the equilibrium point, and the bob will gain speed as it is transitioning towards its center point. The acceleration is not uniform. As the angle theta becomes smaller, the restoring force becomes smaller until the equilibrium point where the acceleration is 0. It's 0 because, remember, it's switching directions now. At the equilibrium point, the bob has reached its maximum speed. As it passes through the equilibrium point, the restoring force now acts to slow the bob down. So it'll accelerate towards the center when acceleration becomes 0, and it starts to transition to a negative acceleration and slows down until it reaches the same height, technically, on each side. Okay. All right, it's very important to note that since acceleration is not uniform, you cannot use these equations in this case, okay? So such equations assume that we have a uniform acceleration. We do not have uniform acceleration here. So to deal with non-uniform acceleration, we require calculus or conservation of energy. And so we're going to use conservation of energy, obviously not calculus, to determine some speeds. All right, so determine the acceleration of a 0.25 kilogram pendulum bob as it passes through an angle of 16 degrees to the right of the equilibrium point. First thing we need to do is draw ourselves a free body diagram for this. So our bob is connected on a pendulum here, and we'll draw in our angles. This is 16 degrees. Continuing with our free body diagram, we have a tension force, And we also have the gravitational force. We need to break our gravitational force into its components. So we're going to break it into Fg and Fgx. And this was Y. You can also call this, I called it Fg parallel and Fg perpendicular. It doesn't really matter what you label them, just label them as something. Okay, so we can find Fg. So let's solve for Fg. The mass is 0.250 kilograms. So mg and I got negative 2.4525 newtons. So if we want to solve for Fg, I called it parallel in my notes, so I'll go with that. That would be the hypotenuse, so 2.4525 newtons times cos of 16. Again, because this angle is 16 degrees. And I got 2.357 newtons, and Fg perpendicular is 2.4525 newtons times the sine of 16 degrees. And I get 0.6760 newtons. Now, we weren't asked to find the tension force, so we don't actually need the perpendicular one. Okay, again, because I'm not looking for tension force, I know that Ft plus Fg parallel is equal to 0. It's not accelerating this direction or this direction. So we need to look at Fg of x. So or Fg perpendicular. So the bob is accelerating towards its center point because of this. Therefore, F net is equal to the Fg perpendicular. F net is mass times acceleration. And Fg perpendicular was 0.6760 newtons. So we're going to sub in for our mass times our acceleration. And we should find that our acceleration is 2.7 meters per second squared. We should include some directions here because it's an acceleration. So we could say that it is accelerating towards the center or equilibrium. You could also say that it is accelerating 2.7 meters per second squared left. Because it was pulled to the right, we could call that left. And if that was the case, we should define our positives and negatives. Because we're not working exactly north-south, we have to define that. And so we'll just use positive, positive, negative, negative. Technically, if that was the case, our Fg was negative because it's accelerating this way. And that's how we would have gotten a negative acceleration to show us that it was going left. All right, so the pendulum, looking at its mechanical energy. So I'm going to read through all of this because I think it's important and shows a lot of connections. We can also understand the motion of a pendulum as an example of the conservation of mechanical energy. When a pendulum is pulled to the side, in this case, position A, the pendulum is given gravitational potential energy, i.e. point A is higher than point B. When the pendulum is released, the gravitational potential energy is transformed into kinetic energy until at the bottom here, all of the gravitational potential energy is used up and it is converted into kinetic energy. The pendulum will continue to swing through this equilibrium position, starting to lose kinetic energy as it gains gravitational potential energy. Assuming that there is no lost heat, friction at this point, it will regain gravitational potential energy. I guess friction would also include the air resistance that this creates. Okay, so assuming there's no loss due to heat or friction, it will rise to a point equal to the original height. And at the top of this, it is instantaneously at rest and all of the energy is in gravitational potential form. It will then begin to swing back towards the equilibrium position and start all over again. So they've plotted it in this handy little graph. So position A, B, and C are noted here. At position A, we have our maximum amount of gravitational potential energy. As we move towards position B, we lose gravitational potential energy to 0. From B up to C, we gain gravitational potential energy again. At position A, we have no kinetic energy. It is not moving for an instant at the top there. It will start to gain kinetic energy until it reaches a maximum, and then it will continue to lose kinetic energy or slow down to point C where it stops again. So at any point in the graph, we could add these two pieces, so the potential and kinetic energy, and they would always equal the same total, no matter where they are. We can find what that value is at these zeros because we know that one of these will be 0, the other is at its maximum. They should always add to those same two values. All right. So we're going to use that idea that the energy sources are equal to solve these problems. All right. When a 2 kilogram mass on a string is pulled so that the mass is 1.274 meters higher than the equilibrium point, when it is released, what is the maximum speed that the pendulum will have during its swing? So I listed out my initial and final energy like we used to in our conservation of energy topic. So the initial energy, what it has as it begins, is gravitational energy. All of that gravitational energy in the final glance at this is turned into kinetic energy. Therefore, our initial energy must equal our final energy. Our initial energy was gravitational and our final energy was kinetic. So just subbing in those formulas, mgh is equal to 1/2 mv squared. Again, these are all scalar values, so we don't have to put in our negatives for gravity, and our masses cancel. We actually don't need it in this respect because they have mass on both sides. I can divide it out. So 9.81 meters per second squared times the height, 1.274 meters, is equal to 1/2 v squared. When we solve, I get that v is equal to 5 meters per second. And it's speed, not velocity. We don't need to include a sign or a direction. What is the speed of the pendulum when it is halfway down from its maximum height? So if it had a maximum height of, I don't know, I think it was 1.274 meters, meters. If it's halfway down from there, it would be at a height of 0.637 meters. So I think that there's two ways to solve this. What I did is I said, okay, let's go back to our initial energy and our final energy. Initially, all it would have is gravitational potential energy at this point. Halfway through its swing here, it has both gravitational. It's still higher than its final position at the bottom, but it also has kinetic. And so I labeled this as gravitational half. So initial energy is equal to final energies always. So gravitational, EG, or potential, if you will, is equal to EP. I'm going to use P, sorry. That is my constant. EP at 1/2 plus EK. So I'm going to call this EP initial, if you will. So mass, gravity, height, initial is equal to mass, gravity, height at half plus 1/2 mv squared. Again, mass appears in every term, so I can cross it out and simplify. 9.81 meters per second squared times 1.274 meters initial height is equal to 9.81 meters per second squared times the half height plus 1/2 v squared. I like to sub in like this, and then I just rearrange it and solve. In this case, I calculated out each side, so 12.49794 joules is equal to 6.2489 joules plus 1/2 v squared. Solving for v, I got 3.535 meters per second. Because I didn't use the mass, I can just use the significant digits from the height. What you could have also said, I have an or in my notes here, is that the kinetic energy at half is equal to the potential energy at half. And go through and solve this way, and you're going to get the same velocity in this case. All right, so we looked at pendulums. Let's look at springs. So like a pendulum that we discussed above, we can understand the motion of a mass spring system as an application of dynamics, so forces. Consider a horizontal mass spring system as shown to the right. If the mass spring system is compressed to the left, a restoring force is produced to the right to result in acceleration towards this equilibrium point. The acceleration may be calculated using a combination of Hooke's law. So the net force will be the spring force accelerating it towards the center. So F net is equal to MA, and F of S is negative KX. So we can find the acceleration of our spring using this formula. All right, as the mass moves towards this equilibrium point, so it was compressed to here, as it moves towards the equilibrium point, the restoring force and acceleration decrease while the speed increases. Again, its acceleration is decreasing because it turns to 0 here, and its direction changes in this case. As the mass moves through equilibrium point, no compression or tension exists in the spring. Therefore, the restoring force and acceleration are 0 when the speed is at a maximum. So it's moving the fastest here. Once the mass passes beyond the equilibrium point, the spring begins to stretch, resulting in a negative restoring force and the acceleration towards the equilibrium point. So the acceleration becomes negative as we pass equilibrium here, and the mass will slow down until it comes to a stop, and then, once again, moves towards the left. Note the negative sign in the acceleration equation above. If the mass is given a positive displacement, the resulting acceleration is negative. So if we stretch it to the right, the acceleration is this way. It's going to accelerate that way. If we compress to the left, that would be negative. The resulting acceleration is positive. In other words, the restoring force and the restoring force and therefore the resulting acceleration is always towards the equilibrium point of the system. Like the acceleration of a pendulum, the acceleration of a mass spring system is not uniform. Therefore, again, we cannot use those velocity formulas for kinematics. So in order to calculate the speed of a mass at any given point, we need to apply the principle of conservation of mechanical energy. So a 0.724 kilogram mass is oscillating on a horizontal frictionless surface, okay, attached to a spring that has this spring constant. What is the mass's displacement when it has an instantaneous acceleration of 4.1 meters per second squared left? So we know that Fs is equal to F net. So negative Kx is equal to the mass times acceleration, negative 8.21 newtons per meter. All right, X is what we are looking for here. And we have our mass, 724 kilograms. And its acceleration is towards the left. Therefore, it is a negative acceleration. When we solve, we get that X is positive, in this case 0.362, and that will be meters. Therefore, the spring is stretched 36.2 centimeters. A vibrating horizontal mass is very similar to a pendulum. When the spring is at rest, its equilibrium position will have no energy. However, displacing the mass from the equilibrium point gives the spring potential energy. When the mass is released, the spring potential is converted into kinetic energy. In turn, the kinetic energy is then converted back into spring potential, which is converted into kinetic, and so on. So like a pendulum, a weighted vibrating spring has a constant total energy, where the total energy in the spring is the potential and kinetic at that moment. And so at the ends of its vibration, the displacement is at a maximum, so X is maximum, and the system is instantaneously at rest. Therefore, we know that the maximum amount of potential energy is equal to 1/2 kx maximum squared. And the total is, when it's at its equilibrium point, it has its maximum amount of kinetic energy, which is 1/2 mv squared. So a 0.4 kilogram mass vibrates at the end of a horizontal spring along a frictionless surface. If the spring force constant is 55 newtons per meter and the maximum displacement or amplitude is 15 centimeters, what is the maximum speed of the mass as it passes through the equilibrium point? So it sounds like we have stretched the spring. So initial, we have potential energy, but rather than gravitational, this is spring. And our final energy is going to be kinetic. It's going to all transfer to kinetic, and we're going to find the maximum speed. So initial energy is equal to final energy, and our initial energy was EP spring, and our final energy is EK. Now, again, our spring energy formula is 1/2 kx squared, and our kinetic energy is 1/2 mv squared. I could multiply both sides by 2 and cancel out the 1/2, so why not? Subbing in what we know, we have 55 newtons per meter as K, and the maximum displacement is 15 centimeters, so 0.15 meters, and that's squared. This is equal to the mass of the spring, 0.40 kilograms, times the velocity squared. Solving this out, we get 1.8 meters per second is the maximum speed as it passes through the equilibrium point.